Welcome, my dear student friends. Today we are going to continue the robotic control system, part 4, okay, in which we are going to discuss the uh, various control algorithms as well as starting from the control of a single joint robo, right? A robo arm can exhibit a number of different behaviors depending on the task and the environment. It can act as a source, okay, as a source of programmed motions for tasks such as moving an object from one place to another place or tracing a trajectory for a spray painting gun. Okay, it can act as a source of forces as when applying a polishing wheel to a workpiece. Right? A task such as writing on a chalkboard. Okay, say you consider a chalkboard. It must control the force. The robot writing on the chalkboard, it must control the forces, right? In some direction, some direction. The force must press the chalk against the board, okay? And the motions in others, the motion must be in the plane of board, in the chalkboard, plane of the chalkboard. When the purpose of the robot is to act as a haptic display, rendering a virtual environment. Okay, we may not, we may want it to act like a spring or damper or mass. Okay, that's why that is yielding in the response to force applied on it. That's why we model the robo arm in terms of mass, spring, damper. Okay, so basically it becomes a second order system, right? So in each cases, it's the job of a robo controller to convert task specification to forces and targets. Okay, torques at the actuators. Okay, it converts forces into torques. Okay, at the actuators. Control strategies that achieve the behaviors described above are known as motion control, right? The behavior, whatever we achieve, is nothing but the motion control. Clear? Motion control. Force control, motion control, force control, hybrid motion and force control, or impedance control. Which of these behaviors is appropriate depend on the both task and the environment. Okay, task and the environment. For example, force control goal makers. Okay, so force control goal makes, right? Since when an end effector is in contact with something, but not when it is moving, not when it is moving in free space. We also have a fundamental constraint imposed by control of motion, okay, and motion and force in some direction. Okay, if the robot imposes a motion, then the environment will be in will determine the force, right? And if the robot imposes a force, then the environment will determine the motion. Understand or not? If a robot imposes a motion, okay, the robot imposes a motion, the environment will determine the force. If the robot imposes a force, then the environment will determine the motion. Okay, understand or not? So basically, the control system behavior. Let us see in a block diagram representation. Okay, so control system, robotic control system, right? So what is inside in the control system? Say a controller, okay, then amplifiers, actuators, and the transmissions, then dynamics. Okay, so this is controller, amplifiers, okay, actuators, and transmissions. Okay, so then dynamics of arm. So this is nothing but dynamics of arm and environment. Understand? So the here in the dynamics model, dynamics of arm and the environment, the forces and torques here forces and torques are applied to the dynamics. Forces and torques. Forces and torques. Here the actuators, both direction, it employs high power control. So here high power control, right? So the here local feedback. This is a local feedback. Right? So from the dynamics, the sensors. Okay. Sensors are the feedback. Sensors are the feedback. So input to the controller is a desired behavior. Whatever we desired, that is the behavior. Here, desired behavior or trajectory. Okay, desired behavior. Set point, like set point. It's called a set point behavior. Right? Desired behavior. Here, low power controls, which is fed to amplifier. So low power controls feed to amplifier. Low power control. Okay. So here from the feedback, the motions and forces are the sensed by the sensors, right? So this is the robotic control system diagram. So controller, amplifier. So amplifier input is low power, output is high power. There is a local feedback to the actuator and transmissions. So this is fed to the dynamics of the robot. Clear? So in here, you see, in the inner loop is used to help the amplifier and the actuator to achieve the desired. So first point is in inner loop is used to help the amplifier and actuators to achieve, okay, to achieve the desired force or torque. For example, DC motor amplifier in torque control mode may sense the current actually flowing through the motor and implement a local controller to better match the desired current, right? So in a DC motor, amplifier in torque control mode may sense the current actually flowing through the through the motor and implement a local controller to better match the desired current. Since the current is proportional to the torque produced by the motor, alternatively motor controller may directly sense the torque, okay, by using a strain gauge on the motor's output gearing, okay, and close a local torque control loop using the feedback. Understand or not? So the dynamics of joint is again considering say mass, damper, and the dashpot. Okay, mass, spring. Okay, so a damper and mass. Okay, mass. So it generates the torque angle. Okay, so it is displacement. Okay, displacement. Sometimes it is xc or theta e. So force or torque applied on the motor. Okay, if it is translational displacement, rotational means angular displacement theta. Understand? So from this we can write the dynamic equation m theta e double dot. Double dot means d square theta e divided by dt square plus dashpot. Okay, this dashpot b theta e dot plus k theta e equal to force. Okay, in the limit as the mass approaches to zero, some in the limit. Okay, when mass approaches to zero, the second order dynamic can become a first order dynamic. Okay, so the mass becomes zero, the second order dynamic becomes first order dynamic. B theta e plus k theta e dot, this is dot ke equal to force. So this becomes the first order dynamics. Okay, first order dynamics. So what is the first order dynamic? So the robo in first order dynamic. First order dynamics. Okay, so what is first order dynamics? So the f, when f equal to 0, we can write when f becomes 0, with 0 the previous equation, this equation, when theta if f becomes 0, this can be written as theta e dot t plus k by b theta e equal to 0. So theta r theta e okay, theta r theta e dot of t plus 1 by t theta e of t. Okay, theta e of t. This can be equal to 0, where actually b by k, this can be written as this can be put as a tau, not the t. So we can differentiate from this t. So this tau where tau equal to b by k. Okay, so 1 by tau. Understand? So this is a first order differential equation. The solution to the equation, solution to this equation, solution to the above first order differential equation. Okay, differential equation is theta e of t equal to e power minus t by tau. Okay, t by tau, then theta e of 0. So this is the solution. Okay, so here for different time constants, so the ratio between theta e of t divided by theta e of 0 Okay, zero dynamics equal to 0.02. That is for settling time for 2% tolerance. This is for settling time. Settling time for 2% tolerance becomes 0.02. So this can be equal to e to the power minus t by tau. So if you equate this, actually for various tau values, so this becomes so for various values. Okay, as tau decreasing. Okay, so what is tau? Tau is a time constant. Tau decreasing. This is 1. This is 0. Okay, this is 0. So theta e. Okay, for decreasing this, the first order response for 3 different time constant. Say tau 1, tau 2, tau 3. So tau 1 is lesser than tau 2, lesser than tau 3. Okay, so that for different time constants. Solving we get finally, already studied in control system also. By taking log on both sides here, so 0.02, actually 0.02 equal to e to the power minus t by tau. Take log, apply log on both sides, natural log 0.02 equal to minus t by tau. So this become equal to 3.91 tau. Okay, so t equal to t becomes 3.9 times tau. This is a settling time for 2% tolerance. Settling time for approximately settling time for 2% tolerance equal to 4 times tau, time constant. Okay, the response gets faster as the spring constant k. The response is faster. Okay, response is faster as spring constant k increases or damping constant. Okay, damping constant b decreases. Okay, decreases. Understand or not? So let us see. So this is single arm. So single joint robo rotating under gravity. Okay, rotating under gravity. Say this is so this is R. Let us consider this R. Okay, so here this is theta. Okay, so this is from this the gravity force due to gravity mg acts here. Okay, so a single joint rotating single joint robo rotating under gravity, right? The center of mass indicated by the checked disk. So this is the center of mass, say checked. Okay, consider this a checked box. So this indicates the center of gravity. Okay, center of gravity. This is center of gravity. Okay, indicates center of gravity. So this is a motion control of a single joint. Motion control of a single joint. Understand? Single joint. So consider a single motor attached to the joint, single joint. So okay, shown in figure. Okay, the motor tau is the, let us consider, tau is the motor torque, okay, and theta be the angle of the joint, theta be the angle of joint, understand, angle of the joint, okay, joint link, okay, joint link be the angle of the joint link. So the dynamic can be written as, I've already discussed the dynamics in the previous class. The dynamics of the joint or link can be written as clear. So tau, tell me what is the expression for tau from this diagram? Expression tau equal to mass of the link and theta double dot plus mg or cos theta. Okay, so cos theta, it is the effective. Okay, from this angle, so cos theta, where m is the scalar inertia, where m is the scalar inertia, okay, and scalar inertia of the link, understand, link about the rotation, link about the rotation, okay, whereas small m is the mass of the link, small m is the mass of the link. Idea? Understand or not? So r is the distance from the axis to the center of mass of the link. Okay. So r is the distance from the axis. Distance from the axis to the center of mass of the link. Center of mass of the link. Center of the mass of the link. Understand? Clear? So and G and G, okay, G can be greater than or equal to 0 is the gravitational acceleration. Okay, gravitational acceleration. This is acceleration due to gravity. This is very well known. All of know, right? So according to this model, this previous equation model, according to this equation model, this is the equation, say equation number 1. According to the equation number 1, there is no dissipation. Okay, so there is no dissipation. Clear? So if the link were made to move and tau were then set to 0. Okay, so if the link were made to move, okay, and tau when set to 0, the link would move forever. So this link will move to forever. Okay, so this is unrealistic. Of course, there is a bound to be friction at the various bearings and gears and transmissions. Okay, so friction modeling is an active research area nowadays. Okay, active research in the robotic field. But the simple model, whatever we consider, but simple model, we can have rotational friction. Okay, so the simple model in simple model, simple model, the rotational friction is due to viscous friction forces. Viscous friction forces, right? Friction forces. So that we can write tau friction equal to b theta dot. This can be written as tau beta dot. So this is equation number 2. Okay. So where b is greater than 0, adding friction torque, adding the friction torque, our final model will become, okay, our final model is tau equal to m theta double dot plus mg or cos theta plus, we are adding the friction here, b theta dot. Okay, so we may write more comfortably. We may write more comfortably as, so equation number 3. So we can write more comfortably as tau equal to m theta double dot plus we are introducing a term h of theta comma theta dot, h of theta comma theta dot. So this is the more comfortable format for the torque. Clear? So where h contains all the terms that depend only on this h, contains all the terms which depends on only the state, okay, not the acceleration. So it consider only, depends only, okay, depends only on the state, state of the state of position, okay. Not it depend, it independent of acceleration, okay. So not acceleration, depends not acceleration. Clear? So for concreteness we can have some typical values. If you want to simulate these equations, so we can have a better values for set. We can set for concreteness as m equal to 0.5 kg meter square. So small m equal to 1 kg. Then r equal to 0.1 meter, 10 centimeter. Okay, and b equal to 0.1 Newton meter second per radian. Okay, Newton meter second per radian. Clear? So in some examples link moves in horizontal plane. So some examples, sometimes the link moves horizontal plane. When the link moves in horizontal plane, horizontal plane, okay, plane. So g value equal to 0. In some cases the link moves in vertical plane, okay, in a vertical plane, plane vertical plane. In that case, vertical plane g equal to 9.81 meter per second square. Understand? So this is the typical concreteness conditions, the values for the modeling. We can simulate. We can simulate using this parameter. We can simulate the mathematical equation using this parameter. We will get the nice response, right? Understand? Okay. Next, we see feedback control. Okay. So what are the various feedback control? First we see PID. PID control. PID control. A common feedback controller. This is the normal feedback controller for industrial applications. Okay. So this is a linearly proportional linear PID control, right? So the PID control, simple PI equation, we already discussed in the previous class. So now we are going to add the we are going to add the term proportional to the time derivative of the error. Okay, so this can be written as tau equal to Kp times theta e plus K times the integral of theta e of dt plus Kd times, okay, derivative times theta e dot, okay, theta e dot, where the control gains Kp, Kd are positive, okay, where this Kp control gains Kp, Ki and Kd, okay, Kd are positive. Understand? Okay. The proportional gain acts as a virtual spring. Okay. The proportional gain Kp acts as virtual spring. That tries to reduce the position error. That tries to reduce the position error. Understand what is position error? Theta e equal to theta d minus theta. Theta d minus theta. This is the position error. Understand? Position error. Understand? Right. So we can have the PID control diagram. PID control diagram. So the okay. So this addition plus, this also plus. Okay. So this is Kp proportional gain directly proportional to the theta e. So theta e. So this is the arm dynamics, the sensor feedback from this arm dynamics. Clear? So this is the theta d desired position. This is the error. This is the actual position. Arm dynamics. This arm dynamics. We already discussed the various arm dynamics in the previous classes. So this is the integral controller theta t. So this is Ki. This is the derivative d by dt of Kd. Clear? So the direction while drawing the block diagram, direction is very important. Don't forget to put the direction. Okay. So this is plus, this is minus. So all pluses, right? So this is the block diagram of a typical PID controller for robo. So robo controller. Clear? So the derivative here, the KD acts as virtual damper. Okay, the KD, see KP acts as the spring. Okay, this acts as spring. Okay, this acts as the virtual spring. KP acts as virtual spring. So spring is linearly proportional. So virtual spring. Okay, this KD acts as damper, virtual damper. So virtual damper, this tries to reduce the velocity error. So this responsible for tries to reduce velocity error. Velocity error. What is velocity error? So there's nothing but theta dot E equal to theta dot D minus theta dot. So this is velocity error. Okay, derivative error. So the integral gain, okay, the integral gain, this Ki, okay, the integral gain, it can be used to reduce, this can be used to reduce or eliminate. We can have eliminate, reduce or eliminate the steady state error, steady state error. Okay, so this is given in the block diagram. Okay, next controller is PD. PD control. PD control. PD control and the second order error dynamics. Second order error dynamics. Okay, error dynamics. So what happened if you use a PD control? Okay. Okay. For now, let us consider the case where K is 0. So when Ki is equal to 0, this is known as the PD controller, absence of integral controller. Okay, let us assume the robo moves near horizontal plane. Okay, so let us assume the robo moves in horizontal plane. So in that case, what is G? G equal to 0. Substituting the PD control law into the dynamics, so we'll be having, so the previous case we have velocity error, position error, everything. So we get substituting the PD control law into the dynamics. So it becomes m theta double dot plus b theta dot equal to Kp times theta d minus theta plus Kd times theta d dot minus theta dot. Okay, we are introducing the law. Okay, the dynamics in the law. If the control objective is the set point control at the constant theta d, so the control objective is the set point control. Say if set point control at a constant theta d with theta dot d with the theta dot d equal to theta d double dot equal to 0. So if we have a constant when the set point control at a constant theta d with theta d dot equal to theta d double dot equal to 0. Okay. In this case, then theta e, then theta e equal to theta d minus theta, and theta e dot equal to minus theta dot, because theta d dot is 0. Okay. Similarly, theta e double dot equal to minus theta double dot. Okay. So then this equation, this equation can be rewritten as, okay. So the equation, say this equation is number say 1. From this chapter, this 1. So if you substitute these values in the equation, dynamic equation, then this equation becomes m theta d theta e double dot plus b plus k, b plus kd into theta e dot. Okay. Theta e plus kp times theta e equal to 0. So you will be, this can be rewritten as in this form. Understand? So in a standard control system form, we can make this equation into standard second order control form. What is second order system? S square plus 2 zeta omega ns plus omega n square equal to 0. This is the second order characteristic equation. Okay, dynamic characteristic equation. Understand? So we please please do it. Make this equation into the form. This equation into the second order form. So what is the second order form? Theta e double dot plus. So divide this thing by m. Okay. So entire equation divided by m. So b plus kd by m into theta e dot plus kp by m theta e equal to 0. Now compare this equation, these two equations. So what are the omega n square and zeta? So first compare these two terms. So this term. So omega n square equal to kp by m. So omega, natural frequency of the oscillation, omega n equal to square root of kp by m. Similarly, compare this and this equation, this coefficient. So 2 zeta omega n equal to b plus kd by m. So omega n is square root of, here it becomes square root of m by kp. So this goes there. So divided by 2. Okay. So zeta. So finally zeta becomes b plus kd divided by 2 root of kp m. So this is the damping coefficient of the second order system. For stability, now stability is another important point. For stability, so what should be the parameters? For stability, b plus kd and kp must be positive, and kp must be positive. Understand? So positive. Clear? If the aerodynamics depends equation is stable, if error dynamics, okay, dynamics equation is stable, then keep in your mind, then the steady state error is 0. Then the steady state error is 0. Understand? For no overshoot and for fast response, for no overshoot and fast response, for no overshoot and fast response, KD and KP, and KP should be chosen. KP should be chosen to satisfy the critical damping. Okay, satisfy critical damping, that is zeta equal to 1. This is for no overshoot and fast response. KD and KP should be chosen to satisfy zeta equal to 1. For fast response, KP should be chosen as high as possible. Okay, subject to the practical issues such as activator saturation, undesired rapid torque changes, that is called chattering. Okay, or vibrations of the structure due to unmodeled flexibility in the joints. Clear? So KP should be for fast response. For fast response, KP should be chosen. Okay, KP should be chosen as high as possible. As high as possible. But that is subject to the practical issues such as structure due to unmodeled. Okay, unmodeled. The problems are unmodeled. These are the issues. Unmodeled flexibility. Okay. Flexibility. Then undesired rapid changes in torques. Undesired rapid changes in the torque. Rapid torque changes. This is called chattering. Okay, chattering. And vibrations. Okay, and the vibrations of the structure due to the unmodeled flexibility in the joints and links. Okay, joints and links, as possibly even instability due to the finite zero rate frequency. Understand? This is about the PID control of second order dynamics. Next, we are going to add one more parameter. It creates the third order dynamics. So that's why it is called PID control and third order dynamics. Third order error dynamics. Third order error dynamics. Clear? So now consider the set point control where the link moves vertical plane. Okay. So now consider for set point control. Our objective is to set point control. Okay, set point control. Set point control where the link moves vertically. So link moves vertically. Okay, when moves vertically, G should be introduced. G is greater than 0 when it moves in a vertical plane. Okay, link moves in vertical plane. Understand, my dears? Okay. With the PD controller, we have to introduce the integral controller in the error dynamics. Okay. In the previous equation, we have to introduce the integral term in the controller. So the error dynamics can be now written as m theta e double dot plus b plus kd theta e single dot plus kp theta e. This should be equal to mgr cos theta. Okay, so mg or cos theta. So this implies that the joint comes to rest at a configuration theta satisfying Kp theta E equal to. Okay, this implies joint. Okay, this implies the joint comes to rest at a configuration theta. Okay, when theta satisfying Kp times theta E should be equal to mg or cos theta. That is the final error. Okay, that is the final error. Final error. Theta E is non-zero. So non-zero when theta D should not equal to plus or minus pi by 2 when it moves vertically, so that when theta D desired torque is not equal to the 90 degree. Okay, the reason that the robo must provide a non-zero torque to hold the link at rest at theta equal not equal to plus or minus pi by 2. Okay, so but the PD control law creates a non-zero torque at the rest only. Okay, the PD control law. Okay, when theta E is not equal to 0. When theta E not equal to 0. Clear? We can make this steady state error as small by increasing the gain Kp. But there are some practical cases in the previous DC. So there are the practical cases: unmodeled flexibility, undesired rapid torque changes, chattering and vibrations. So these practical issues are there, practical limits. So to avoid the practical issues, clear? So the PD controller avoid the practical issues. To eliminate the steady state error, we can return to PID control. So in the previous controller, I explained that the integral controller eliminates the steady state error. So to avoid steady state error at the final error, we introduce the PID integral controller in the PD control, right? So now this can be by setting ki integral gain is greater than 0. This allows non-zero steady state torque even with the position. This implies the non-zero steady state error. Okay, steady state torque even with the zero position error. Understand? Zero position error. So only the integral error must be non-zero. Only error. Only the integrated error must be non-zero. Must be non-zero. Clear? So say I will show you the response between the comparison between say we can have it say this is 0. Say the PD control. This is the PD control response, whereas the PID control create the 0 response. Clear? So this is 1. This is 0 position. So this is theta E. Okay, theta E. See, this is the PD control. PD control with steady state error. PD control. So this is PID control. PID control. Clear. So this is a tracking error for PD controller. With the, this is the typical plot. Okay, this is typical plot with the PD control. PD control. What is the PD control dynamics? So PD control with KD equal to 2 Newton meter second per radian. Okay, and KP, the position controller, equal to, this is a typical plot for this thing. So Newton meter per radian. Understand? For zeta equal to 1, critically damping. And for PID control, for this PID control, the KI, we introduce KI equal to 1 Newton meter per radian second. Okay, radian second. So the arm starts at the arm. Here the arm starts at theta of 0 starts theta of 0 equal to minus pi by 2, comma theta dot of 0 0. Okay, with the goal state, with the goal state, theta d equal to 0, theta dot d equal to 0. Okay, so the individual contributions of the terms KP, KI, KD are different, right? So this diagram demonstrates the effect of adding integral controller with the PID. So this is the effect. So you can see from the two responses. Okay. So this how works. We can see, we can explain with the dynamics. This how works. Okay. So let us consider the dynamic equation, error dynamic equation plus B plus KD theta E dot plus KP theta E plus, now introducing theta E of T dt equal to torque disturbances. Okay, so torque disturbance. So the tau dist is nothing but torque disturbance, disturbance torque. Okay, that substituted for the gravitational term. So this is a disturbance torque, which is replaced for, this is replaced for the term gravity term. So what is the gravity term when it is moving in the upward? Mg or cos theta. This is the gravity term. Okay, so taking the derivatives of both sides, we apply derivatives of both sides. So taking derivatives, right? Derivatives on both sides, So m theta E 3 dot. Okay, so you can have a 3 dot, third order dynamic, plus V plus KD theta E double dot. Please observe this, plus KP theta E dot plus KI theta E equal to tau dot disturbance. Okay, so this is the derivative term. Okay, if the disturbance is constant, okay, if tau is constant, tau disturbance is constant, constant, Then what happened if tau decibels constant? Then right hand side RHS becomes 0, right? Right hand side becomes 0. So then apply Laplace transfer function. Finally convert it into standard format. So this equation becomes say in this say SQ plus B plus KD by M, B plus KD by M S square plus KP by M S plus KI KI by M equal to 0. If all the roots of the equation, all the roots of this equation have negative real part, so all the roots of the equation, roots of the equation, this equation, the equation have negative real part, negative real part, real part. Then the error dynamics is stable. Then because it lies on the left half of the S plane, then the error dynamics, okay, dynamics is stable, okay. Then when it is stable, the theta e converges to 0, okay. The theta e converges to 0, understand, converges to 0. Here why disturbance torque due to gravity is not constant, okay. Disturbance torque tau disturbance, okay, due to gravity is not constant, understand, is not, gravity is not constant. What happened? Constant, okay. As the constant, as the link rotates, as the link rotates, as the link rotates, it approaches a constant theta dot goes to 0, okay. It approaches, okay, a constant, understand, a constant theta dot, okay, theta dot goes to 0, understand, goes to 0. So and therefore similar reasoning holds close to the equilibrium, close to the equilibrium, that is theta e also 0, that is close to the equilibrium, understand. So the each term contributes when it is rotating, okay. A goal state, I will explain with the diagram. Say this is the response for different controllers for different position when it is rotating. You see the P term, alone, okay, the P term alone moving, creating a offset, constant error. So whereas D term, okay, D term has negative error and settled at the side. So this is a D term, this is P term. Similarly, P term for the controls, okay, when it is controls, P term, this is the P term, whereas whereas I term has this I term. So again D term, clear. So when the arm, so let us see the arm positions, the rotation of the arm for the different positions. So this is the arm. So the arm is horizontal when it is moving horizontal. So the same arm okay. So this is the center of gravity point. So the desired configuration. So this is the desired configuration. Desired configuration equal to PID configuration. PID configuration. So this is PD final configuration. PD final configuration. This is the initial configuration. Initial configuration. Okay. So G acts here. G. This response P term. This response D term. This is I term. This is P term. This D term. Clear? So as a goal state, theta D equal to 0. Theta dot is also 0. So that is the middle case. Okay. The individual contributions in terms of PD control for various laws. Here you see the non-zero integral, non-zero I. Okay. Term for the PID controller shows the P proportional term to a drop to 0. It drops to 0. This is the PID. PID. This is PD alone. That is PD alone. This PID. So the initial and final configurations with the center of mass indicated in the check disk. Okay, check disk. For all the roots of equation, whatever I mentioned here, this is the root for all the roots of equation. This case. So see that equation. Let us write here. So the for all the three roots of equation S is Q plus B plus KD by M S square plus KP by M S plus KI by M equal to 0. Okay. So the roots of the equation have negative real component. The following conditions on the control gains must be satisfied for the stability. What are the for stability? The condition should be satisfied. Stability. What are the conditions? KD should be greater than minus B. KP should be greater than 0. B plus KD into Kp by M should lie between Ki greater than 0. So these are all the conditions, standard conditions for stability in the third order dynamic equations. The new gain Ki must satisfy both lower and upper. Okay, the new gains, introduced Ki gains, okay, must satisfy lower and upper bound. Okay, must satisfy lower and upper bounds. Okay, upper bounds. That is for bounded input, bounded output. Understand? So must satisfy for the upper bound, which described in the diagram. Okay, which described in the diagram. Okay. So the reasonable design strategy for choosing Kp and Kd for good transient response, and then choose Ki large enough that it helpful for reducing. Okay. So design strategy. Okay, the design strategy for to choose design strategy to choose KP and KD for good transient response, for good transient behavior or response, and then choose KI. Understand? And then choose KI large enough that it is helpful to reducing or eliminating the steady state error. Right? So choose KI large enough. Okay, large enough that it is helpful, that it is helpful for what? Helpful to reduce or eliminate, to reduce or eliminating the steady state error, but small enough that it does not signify impact on stability. Okay, so but it should be small enough that it does not okay significantly impact stability. Okay, that's it's, but does not significantly impact stability. Okay, impact on stability. Understand? Stability. So in practice, if K is 0, many robo controllers, since stability is the paramount. Okay, if okay, in practice, Ki is equal to 0 for many robo controller. Okay, since stability paramount, since stability is the paramount. Okay, many robo controller, since stability is the paramount. Stability is the paramount. Clear? So other techniques can be employed to limit the adverse stability effect of integral controller, such as integral wind-up. Okay, so integrator, anti-integral wind-up. So main drawback with the integral controller is it produces integral wind-up. So we can reduce the adverse stability effect. We can reduce the adverse stability effect using, so we can reduce adverse stability effects on using KI integral controller. We can use we can reduce using effect of KI. We can use integrator anti wind up. Okay, you know what is integrated wind up? Integrated wind up is nothing but it's a very important phenomenon using integrator alone. Okay, so that is the integrator and wind up. Say if you have one, I will tell one small example. Say you use our tap, small tap in our home, the rotating tap. Okay, tap bucket. Say bucket is there. So this is the output valve. Say tap is our home tap is here. So there is a tap. okay, which we normally open and close. It takes a few turns to open and close. So you fix in the bucket. You can realize the integral wind up, integrated wind up here. Say you try to fill the bucket of vessel, okay, this vessel. So our set point is, say, this is the set point. So when the water level rises near to the set point, we tries to close the valve. We tries to close the valve. But when we tries to close the valve, the level little bit comes up. Say comes up. What we do? So we use this out wall to reduce the to reach the correct set point. So when we use this wall, this tap, when we open, if the level falls down. When we open the this tap, when the level falls down, when the level reaches the set point, we tries to close this valve. Okay, this valve. So the moment you tries to close this, it will take few turns. Understand? That is the concept of integral window. So what did happen? The level a little bit falls down because of the wind up in the wall, the tap. Understand? Then what we have to do? Then we start opening this tap, the inlets. This is the inlet tap. This is the outlet tap. So when we tries to fill again, when it reaches the set point, then we tries to close the valve, then it moves up. Understand? So it never settles at the set point when we use the integral. So this type of action is called integrated wind up. Okay, integrator wind up. Okay, so to avoid such unstable conditions, worst conditions, we can go for anti-integral wind up. Understand? Anti-integral wind up. So clear? Understand or not? Right. So the three roots of the previous equation, say, say we can explain with the root locus. In explain, say this is imaginary of S plane. This is a real of S plane. So negative real and other things. So there are three roots. Okay. So three roots on the S plane. So one root at this juncture, another root here. This. Okay. So this root root locus starts from this. Say I will explain with the different color, then you can easily understand. So there are three roots. So one root from here and mingle with here. Okay, one root. Another root from this side, right? From this side to this side. So they take a break here. Okay, take a break and moves to the imaginary axis, crosses the imaginary axis. Similarly, it crosses the imaginary axis. So this is the infinity. It reaches infinity. Okay. So the third root, right? Okay. Understand? So in this moment of three roots of equation, as k increases, as k increases from 0, first a PD controller is chosen with Kp and Kd, yielding critically damping. First, okay. First we choose PD control with Kp and Kd for zeta equal to 1, yielding critical damping, give rise to two collocated roots on the negative real axis. Two collocated roots on the negative real axis. Understand? Adding the adding ki greater than 0 creates a third root at the origin. So it creates as the third root at the origin. Okay, as we increase the third root at the origin. Okay, origin. So as one of the two collocated roots, okay, moves to the left of the left of on the negative real axis. Okay, so as we increase, as ki increases, one of the two roots increase, collocated roots moves to the left of the negative plane, left of the negative axis, real axis, while other two roots move towards each other. Okay, that crosses the imaginary axis. Mean that they meet together. These two meet together. This root and this root meet together and take a breakaway at this point from the real axis. Begin curving to the right, okay, to the right, and finally move to into the right half of the S plane. It crosses through the imaginary axis, so it crosses the right half of the S plane. Clear? So the Ki, you know that already. Ki equal to what? B plus Kd by M into Kp, right? So the system is unstable when it crosses the boundary, the imaginary axis, it becomes unstable. For larger values of for larger larger values of k, it becomes unstable because it crosses the imaginary axis uh, at the crossing point. So it crosses the imaginary axis, becomes unstable. Clear? Understand or not? So this is the major difference between the PD control, that is second order dynamics, and PID control, third order dynamics, right? So this is the very important design concept for robotic controllers. Okay. So thank you very much.